Hey everyone, make sure you check out part 3.5, which is just a quick little video. There should be a card in the top right if you haven't seen it. Basically, we just fix our grammar so that it's actually what I said it's supposed to be. Ironically, that's not actually going to affect any of the code we're writing right now, but it's going to be useful for later. So in this episode, we finally have all of the pieces to start working on our Lexer. So if we just come into this folder, we can create a lexer.kotlin file. If I open up the existing one. Now, this is going to be one of the largest pieces of code that we've written so far. It's kind of... I don't know if I'm in love with the fact that this file is so, enormous. Literally 300 lines. But at least for now, I think this is a decent approach. This sort of thing, right, where we end up with, okay, we have one big Lexer that handles every type of token. That's one of the reasons that our parser is actually going to be completely different from our Lexer. The Lexer will create every single type of token. But when it comes to our parser is just going to be a useful tool, while the nodes themselves, every expression will be able to construct itself using the parser. And you could make your token generation the same. You could have 5 or 6 token classes, each using the Lexer to construct themselves. I've done that in the past. For whatever reason, I've just found that this approach is better because I think I just have one token class, but honestly, that approach might be better overall. But what I'd recommend is, for the most part, just follow along with how I'm doing things. And then once the series is either really past that point, or once it actually ends, you can go back and refactor and make your own improvements. And when you do that, you're going to actually understand the code a lot better, and you're going to make code that you understand even better, which is going to be beneficial for all parties involved. So we can make our package, which will be c.lexer. Now we're going to need Kotlin math.pow for exponents, because we're going to be calculating those custom number bases, like I said. We're going to want access to our faults, c.faults, and we're going to want our token, which is now in the grammar package. Okay, all that seems good. And we can make a data class and call it Lexer. And it's only going to need a handful of things. It needs a faults, so that we can have Lexer faults. And it's going to need a file path, so that we can actually construct the source file that we're going to be lexing right now. So we can go ahead and do that. We can make a file, which is just the source file from before. And we can construct it using the file path. Since they're both in the same package, we don't need to import it. And then we want a list of tokens that we're going to make. And all this is going to be, for now, is a mutable list of type token that it starts empty. Next, we're going to need some helpful functions. You can't see all of them, but let's just start with the toString so that we can print out our Lexer. And when we print our Lexer, all we want are the tokens. So what we can just do is say, take this list of tokens. We can join it to a string so that all the elements can be added into a string. We'll use a comma as a separator, and we can, before all of the tokens, we can have a square brace, and after we can have a closing square brace. So, for example, if tokens is like this, then it will literally print this, as you would expect. Next, actually, I want to go over into this file and go down to, nope, down. I have to go all the way down. We're going to make a new token function. And the purpose of this is we have to pass in a line and a type to make a token every time. And we have to add it to our list. So that's that would be a pain to do every single time. So let's just make a simple function that does that for us. Private function, new token. And just for the sake of character width, This is how I'm formatting it. I don't like it, but I think it's better than being too wide. Also, my bad. I just realized I haven't actually changed this profile so that it's the right font size. If I click on here and then I go to this. All right. Hopefully that's better. I'm sorry that I forgot to do that. And let me just quickly come in here and do the same thing. I have to right click on this one. There we go. Silly me. And now I have to go back down here, and there we go. So when we make our new token, it will take in a type. By default, this should just be the none type, which is kind of the purpose. We just don't care about the type. Usually that will be when we have an error or something. And we want it to pass in a source line, which by default should be the current line of the file. But sometimes we're going to want to pass in a separate line, because specifically once we take new lines, which in our language actually matter because we're going to have optional semicolons, when you take a new line, remember before, when we say like file.take, that's going to change the line if we're at the end of it. So if we take the symbols and then we construct the token, it's going to reference the next line after, not the previous. So what you have to do when you make a new line, as we'll see in a moment, you actually have to store the previous line, take the symbol, and then pass it in when you call new token. But so yeah, this new token is going to return a token. This formatting is kind of atrocious. Yeah, there's not much. You can format it however you like, but this is the fundamental idea. So we make a token using the line and the type. I reverse the line and the type just because the line is the more optional thing here. Perhaps in the token class I should have started with type instead of source line. It doesn't really matter though. Just keep in mind that it's not the same if you ever call the token constructor by itself. So we make the token, we add it to the list of tokens, and then we just return it. Okay, now let me go back up to the top. And luckily we have all of the structure ready, because source file and source line and token, all of those have all those methods and fields and properties that we added. So after we make a new token, well, this is like a utility thing, right? The public sort of thing that you're going to call is make tokens. So you'll have a Lexer and you'll just say make tokens. And all this is going to do is it's going to call make token while you're not at the end of file. And of course, we'll define make token in a moment. Now, the reason I'm doing it this way, well, there's two things to point out, right? I'm using a do while loop, meaning it will call make token before it ever checks this condition, so that even if we're at the end of the file, we'll make an end of file token. And I'm separating make token into its own function because we're going to have other functions that are going to call it in the future. So I think what I'm going to do is I'm going to format it like this so that new token is the first private member, but I'm keeping the public interface like right at the top there. And so now we can define our make token. And this is going to be kind of simple. As you see, we're going to ignore all spaces and comments. We'll handle that in a moment. And then what we're going to do is we're going to say, we're going to loop through the file, right? Character by character. So we can use a when expression to say, when the next character in the file, suppose it's the null character. Well, then we know it's an end of file, right? And we can just say, we can just take that single character, and then we can make a new token, token.type.punctuator. And if you're not familiar with when expressions, they're kind of similar to match statements or switch statements in a lot of languages. This is just the syntax for it. And you see, we don't actually have to store any variables or anything because the class handles that for us. We can just say file.take one thing. We don't care what that is. The file keeps track of that. And then we can just say make a new token of this type, and then the Lexer handles that. We don't have to manually, assign, well, we need this character, and then we have to pass it into the new token, and we have to store the new, like, we don't have to manage that. The state is sort of just managed for us, and we can just work in that framework, which is why I've designed it this way, and why we've had so much in the last 3 episodes before we actually could even make the Lexer. So for now, this is just taking the end of file, and then on the right side, you see there's a bunch of other matching things. We can check if it's in sets of symbols, and then we know what type of token to make. But otherwise, if we don't match anything, well, then we have some symbol that our language doesn't recognize. So we should have an error for the user so that they know that that thing doesn't work, right? So we can take the symbol, and then in this case, we can actually store the token as a variable so that we can utilize it in a moment. We can store that token, and notice it's going to have a default type of none, and it's also going to have whatever this symbol is as its string. Then what we can do is we can throw false.fail, and I consider this a failure because if you have some symbol you've never seen, how can you possibly continue, right? Because the Lexer's job is to make tokens, and there's some symbol here that doesn't belong to anything. We should just stop because something's clearly wrong. But if you want, you could make it an error, and then you could continue if you think that makes more sense. And so we can just give it some message like unrecognized symbol, and then we can say token.string. That's why we had to store a token as a variable in this case. You could say tokens like at the last index or something, but I find this just is the simplest way. And so let's see what we're doing so far. When we do make tokens, we're going to be looping through this essentially until we're at the end of the file. And then right now, all we're accepting is end of file characters, and it should make just that punctuator. So actually, this is probably enough to start testing if this is working. So let's go back up to app.kt. We can import c.lexer. We need source file and Lexer, so I'll just import everything. It doesn't really... It's not... I guess it's not optimal, but it doesn't particularly matter. And now we can actually come in here and we can make our Lexer. And it's just a new Lexer, and we need the false object, and like we said before, we need the file path. In this case, it's the source file path. And now we need to change our run Lexer. So instead of taking the false, it takes in the Lexer. Change that right here. And we had building name of file here. We can access this by saying lexer.file.path, I believe. Yep. We need a false object up here. We can just say lexer.false. And to make the tokens, we can just say lexer.makeTokens. To write out this message now, we can just print out the Lexer because we made the toString. And so this is like a relatively simple. I have to go into YouTube Lang. And let's try running cbash. And as you can see, since our basic file is empty, it just works perfectly. It just makes a list of tokens. In this case, it's a punctuator, end of file. So all of that stuff we set up before is working, at least for me. Hopefully it's working for you as well. If we go into... I have to go all the way back up, go into our docs, no, go into the test folder. And if I add something like a 5 here, just like a number, and then I run it again, you see we get our failure unrecognized symbol 5 because we haven't programmed in numbers yet, but this is showcasing that our errors are actually working. I did misspell unrecognized, but that's okay. We can fix that in a moment. Something else you'll notice is the way we've done things. If there's a failure and we throw an exception, then the Lexer doesn't print at all. So if there were tokens before the failure that were valid, we're not going to see them in the debug thing. You could change your thing so that it works and actually keeps track of things before. You just have to be careful sometimes. In this case with Lexer, I think you easily could. You could just print out the tokens at that point. I don't think I'm going to do that here, but you could. Consider that a personal challenge, I suppose. When it comes to our parser, though, that's going to be a bit harder because you're going to end up with nodes that have like a binary node, right? That has a left and a right, but the right might not exist, and so that could be an issue, so that would be a lot harder to actually handle. But for now, I'm not going to handle that. I think let's just add something in here to sort of... No, we can come in here as we need to. I don't know why my fuzzy finder is being very annoying, so I have to more manually come in and out. So our app should be fine. If we come back in our Lexer, we can add more tokens. So what I want to do is ignore spaces and comments. Okay. Because that's going to be pretty important. Most languages, you're going to want to do that. If you're designing a language that's more like Python, then you'll probably want tabs to matter. And you can do that pretty similarly to what we've done. You just have to be a bit more careful about how you do things. I've done it in the past. It's not fun. It's definitely easier to make a language that doesn't matter in terms of spaces. Especially if you want semicolons, then you can actually just completely ignore new lines, and that makes things even easier. But personally, I like having semicolons be optional, like in Kotlin. So we have our make token, and we can just make the function right down here. Function ignore spaces and comments. And again, I am like separating this a lot more than you might need to. This is just how I think I'm going to do it for the time being. Every time I rewrite it, I'm going to change it slightly. So if you want to change how this works, that's okay. But basically, anytime you call ignore spaces and comments, what you're going to do is you're going to ignore spaces and you're going to ignore comments, because one of the issues I've run into is if you have a file, and let me just quickly give an example. If you have a file like this, where you have a number, and then you have a new line, there's a new line after that, and then you have some comment, and then another new line, and then a 4, you'll end up with 2 new lines, and that makes things really tricky in terms of parsing, because it's just like a mess, because you could have an arbitrary number of new lines. So my solution is to make the Lexer smarter. So if you have a comment, it should be able to essentially make a single new line instead. But we'll do that in a moment. Just get rid of all that. And we actually need our ignore space method. For now, I'll just return false and ignore comment as well. So you see, how this is going to work is we're going to return true from ignore space or ignore comment if we did not. Let me see exactly. It's always hard to remember exactly which one. So yeah, you return true from ignore space or ignore comment if you did ignore something. And the reason for that is, like I said before, if you ignore a comment, you then want to ignore space. So you just loop through this. If you ignore space, then because of the or, this will be true and it will do the while again. And so you'll ignore all your spaces until there's none to ignore, and then it will try and ignore comments. And if you do ignore that, then it will come back and start again, because maybe you have spaces after the comment, or you have multiple comments in a row, etc. This will get rid of all of them. Now, it is called ignore spaces, but this is also where we're going to be constructing our new line tokens. Because, like, as I've said, new lines will actually matter. Nized. That's better. So, let's make our ignore space. This isn't too bad. That the comments are going to be a bit harder because you could have multi-line comments, but that's not too big of an issue. So obviously, if file.next is not, if we don't have white space next, then we should just return false. And so this is just a built-in that checks if the character is like a white space character. So this could be any sort of characters, because remember, white space is not simply just like tabs, spaces, and new lines. You also have like return characters and like all sorts of antiquated symbols that exist because computers used to be a lot more typewriter-esque. And then, so we check if it's not white space, we just leave. Otherwise, we have some white space. So if the white space we have is not a new line, well, then it's just a space or something else that we don't care about. So what we can do is we can just take whatever that thing is. We can then ignore it, which is why we have our line.ignore position. And then we can return true because we took something. You could make this a bit more efficient because technically this is kind of slow, I guess, because you're taking one space at a time. But since we're doing the while loop, calling this function, it doesn't particularly matter. It's not necessarily the most optimized way to do it, but I'm not sure if that is really important or not. So the first case, now we know that there's white space here. And after this, we know that the white space must be a new line. So what we can do is, like I said before, we have to store the previous line, the line that the new line is actually on, and then file.take1. And then that's taking the last symbol, which means if you said file.line here, that's going to be the next line, not the one that the new line character is actually on. That looks kind of nuts, but I think that's a fine condition. So we have to check something. If tokens.last or null, and this is going to get whatever's at the end of our token list. By saying last or null, we're saying if tokens is empty, return null. Otherwise, give us whatever's at the end. And then we can say, well, if this thing isn't null, then we want to check, does this have a new line? And if there was nothing, we can return, we can just set it to false. I'm missing a bracket. I'm just trying to wrap my head around this, but I remember why I have this. This is the thing that enables us to only get a single new line. What we're checking is, we just took a new line, right? But we haven't made the token yet. So what if we have a new line, but the last token that we added is a new line? Well, that means we have two in a row. So what we should do is not make a token. I don't really like this negation, though. We're saying if... So we're taking the last thing. This whole thing, the last or null dot has new line. That will return true if the last token was a new line. So maybe I can actually make this more readable. Last was new line is equal to tokens dot last or null dot has a new line, otherwise false. Because if it's empty, then it's false. So if not, last was a new line, then what we want to do is we make a token. And it will be of token type punctuator, and we give it the line. Otherwise, we ignore it. Let me add another new line in between here. And then we can just return true because we took a new line. So I think that helps make it more readable. Tokens.last or null. If it's not, you could also, of course, write this as something like if this condition would be the same as tokens.size is 0 or tokens.last has a new line. Do I prefer that? That's a good question. Because that's kind of more obvious as to what's going on. Let me take this and see if it fits on the same line. I think I do prefer this. Like, the other one is using some Kotlin stuff, but to me, this is just more readable. Is the size empty? And the good thing here is, if the size is empty, we're never going to call .last. So we'll only call .last if the size is greater than 0. So to me, that's more readable. You can write it either way, though. I think I'm just fine with that. So now that handles all of our spaces. We don't have comments yet. Let's come up here, and we can now say ignore spaces and comments. All right. Now we can actually start ignoring our comments, just like any good YouTuber. And this is simple. There's 2 conditions. And now this is where the next string is going to be super handy. We can say file.nextString of 2 characters. And we can check. Well, is it a single line comment? If it is, we can just take. And what do? We take until we reach the new line. Technically, you don't need to do this because the way we've defined take, it will only take until the new line. Well, actually, if you do it the other way, it will also take the new line as part of the comment. Doing things this way, it will keep the new line there. And that could be useful for certain situations, because imagine if you have 5 + 5 followed by a comment something, and then you have like a 4 over here. If you take the new line as part of the comment, then it would be as if you wrote this, and this doesn't make sense, and that wouldn't parse. So that's why you want to leave the new line here, and that's why you have to specify until. And so we take everything until the new line, and we can just ignore it. Just ignore the position. Otherwise, if we have a multi-line comment, we can say ignore multi-line comment. And I've split that into its own function as well for reasons for the fact that how you can see how huge it's going to be. And if it's neither of those, we can just return false because we didn't take anything. But otherwise, we took one of them, right? We either took a single line or a multi-line, it just fell through, and then we return true because we took something. Now we can take our multi-line comments. And then we can actually start making real tokens other than new lines. But comments are super useful. You don't want to be like Tom, you know, with J Diesel. Comments should be ignored. They should not be ran. So your line is equal to file.line. Since this is a multi-line thing, we need access to the previous line. Okay. We need access to the line that the comment is on. But why? Because we're not making a token. We do make a token, actually, if the comment isn't terminated. So you can imagine, if we did this, that's not good. That just means everything else is, like, a comment. And so we want to detect when somebody has an unterminated multi-line comment, because that's clearly not intended. And what we can do... So what that means is, if we have to throw an error, we need a token to throw the error on. But if we just say new token, the line's going to change as we're taking things from it. So we want access to the beginning of the multi-line token so that we have something, so that we can actually show the user. We can take the 2 symbols that start the comment, and then while we're not at the end of the file, we have to loop. And we have to loop because our take stops at each line, but also because we want to check. So while we're not at the file end, if the next string of 2 characters is not the closing of this thing, then we can just take a symbol. Well, what we can do is we have to... Well, I'll explain this in a moment, but... So we have to take until we get to an asterisk. Why do we do that? Because if there's an asterisk, then maybe we have the closing symbol. So presumably, continue. And this will loop until we get the closing symbol. In which case we'll go down here and close it. But the reason I've done this, the reason I added this extra take one, if we have to take until there's an asterisk. So suppose there's an asterisk next, but it isn't a closing symbol. Then, okay, the next token.next or file.next is going to be the asterisk. We're going to come up here, and this condition is going to be false, so we're going to come down here and loop, and we're going to take, I'm saying if this didn't exist, and we're going to take until an asterisk. Well, the next character is. So we'd end up in an infinite loop. That's why we have to take the 1, so that if the next thing is an asterisk, we take it, and if it isn't an asterisk, it doesn't matter because we were going to take it anyway. So if we do have the closing, we can just take those 2 symbols, and we can ignore everything. Thinking about this, though, now that I'm looking at this, no, it doesn't matter. But something I've realized is, when we're calling ignore position, we're calling it on the line itself, right? So that tells the line to move its position, or to move its start position. So actually, suppose this comment takes up multiple lines. Then we're going to have multiple lines whose start positions were never ignored, but that doesn't matter because we're not constructing any new tokens off of them, so we only have to ignore the current line's position after. And then we can just break out of this if we've done that. Otherwise, we've reached the end of the file, and we have to say that, well, this thing's not terminated. And this is why we needed to construct the line. We need to store the line before. Since we have default arguments here, the type can be none, and we can just specify that the line should be the line that we've stored. We can just say unterminated multi-line comment. And so now we're basically, I think we're done with that. We're taking all of our spaces and new lines. So I have to go back up in the least efficient way possible so that we can add some stuff. So let's add a comment that says this is a comment. And actually, let's sandwich it between some new lines. And let's see what happens. It's only making an end of file. That's interesting. There should be at least one new line here. Interesting. Because I can't add any more symbols yet. Let's go back and let's just take a quick look. Private, we're ignoring spaces and comments. I added in everything there, and I'm calling it every time we make a token. Make sure I actually wrote this file. Yep. Okay. Let me go back up to make token in here. And in fact, let me cheat for a moment and just take 5. You don't have to do this. I'm just going to do this real fast. And we're going to just make a number real fast. So file.take1 and new token. Just so I can play around and make sure that this is actually working. I'd hate to give out code that isn't working. So now our Lexer will temporarily accept the number 5 as the only number in our language. And then what we can do is go back up. Very annoyingly. And now if I add 5 in here, does that fix things? Yes. So the issue was there was just nothing. Is that optimal? I'm curious. That's interesting behavior. I think I know why it's happening. But so see, if we have the 5, it makes the 5 plus the new line after. But when we remove this comment, there's a new line here and a new line here. Well, there's at least one new line that it just doesn't take. If I put another 5 here and another new line, it takes there's only one new line after each of them, even though technically there's 2 new lines after this 5. So that's working as we're intending. And let me do the unterminated comment, and let me show you exactly what I was talking about before. Just some text. That's what? Did I not? I don't think I actually wrote this. Yeah. Also, I want this on a separate line. Okay, that's better. I was freaking out for a moment. But so you see, because we stored the line, it actually has access to the start of the comment. Like I've said before, we're only keeping track of one line per token. You could change that if you have different types of multi-line tokens. The only multi-line tokens we have, well, there's the failure, there's the error token created by a multi-line comment that you're seeing now, and then there's multi-line strings. But the way I'm going to do multi-line strings is going to be separate strings per line, so that should help fix that problem. When it comes to this, though, you could make a token every single line and store them in case there's an error, but then you'd have to clean up after them, and that would be kind of a pain. Anyway, you can see that that is actually functioning as intended. That's fine. So let's go back up, and we can, there's still time, I suppose, in this episode, and we can do some more. Let's actually get some real tokens now. What's going to be, maybe I'll do the numbers now, since numbers are kind of obvious. I am not good at Vim. Okay, if the next character is in the set that we created before, the num start symbols, then we would just want to make a number. And now we can come down here, and we can define what make number is. Notice that, okay, so I'm making numbers before I'm making punctuators. And that is intentional. The other orders don't really matter, but in our case, we do want to make numbers before we make punctuators, and I'll explain why in a moment. Let's go over and go down to make number. It's going to be a bit of a pain. So, the first thing is we're going to use some regular expressions, and the reason for this is to match what our numbers look like. As I've mentioned before, we're going to have different types of numbers. We're going to have, you know, normal integers, and then we can add on periods and do things. But we can also have an arbitrary base to our numbers. Or you could write a hexadecimal number with or without a period in between. So, for clarity's sake, I'm just going to define this D, which is going to define any type of digit arbitrarily, right? Which, in my case, I'm going to have the symbols 0 to 9 and all the capital letters A to Z. And this is a captured group using regular expressions. If you're not familiar with regular expressions, I'd recommend... I'm sure there's some good tutorials on YouTube, but I'll try and explain as I go along in this. Now we're going to make a very big pattern here. And this pattern, it's not going to be a perfect representation of the numbers we accept, but it's going to be a loose checker to try and like rule out as many things as numbers as possible. And we're going to use multi-line strings in Kotlin. And now this is for a few reasons. One, it's so I can format it on multiple lines in a nice way, but also these multi-line strings are somewhat raw strings, meaning every slash you see is actually a slash symbol, whereas if I put a slash here, that's not a slash symbol, that's a slash escaping that, and I would need a second one. So if you do regular expressions in normal strings in Kotlin, you'd have to put twice as many backslashes, which is a big pain. So, we're going to have some different types of things here. The first, we're going to do a /d plus. And so, the parentheses mean that this is like a capture group. The /d means it should be digits. And now this isn't the D that I've defined, this is an existing one, which is letters 0 to 9. Numbers 0 to 9. The symbols themselves. And the plus means one or more of them. So this is going to be all of our integers. These are just like things like this. It's very simple, just one or more digits back to back. Or our numbers could be two things. They could be this, which is the star means 0 or more, meaning there might be none, or there might be multiple. And we want to use a backslash on the period. What that is going to do is that's going to match a literal period, because a period in regular expressions matches any symbol. So we want to make it a slash period so that it is the period symbol. And then we want a /d plus. Now, why exactly am I doing this? I'm doing this because if we do this, right, and we say it should be a star and a star, well, that will match a symbol period. And we don't want that. We want our period to actually make a punctuator. And that's actually why we're making the number before we make the punctuators. So that if there is just a period somewhere, if the thing starts with a period, it could be a number. If we have something like this, if you write 0.5, if we see a period, if we made punctuators first, it would make the punctuator 0 point, the punctuator period symbol, and then it would come and make the integer 5, but that's not what we want. We want to come into make number and say, it starts with a period, a decimal point, and then it has a 5, which is all together one number. And so we do this with the star and the plus so that it could start with no digits. It could start with the decimal point. But then if there are no digits before, there needs to be at least one after. Otherwise, it's not a number. And then similarly, if we want no digits after, which is something I want to support, because a lot of languages you'll do something like this, 2 point, just to make it like a floating point instead of having to specify things. You can choose what you want to support in your language. If there isn't a symbol after, then there has to be one before. So we just have to do this. And I'm just formatting this with spaces so that it's a bit more readable, but after we're going to remove all the spaces from this. Next, there's the arbitrary base matching. And so what this is going to be is well, it's going to be exactly the same thing at first, followed by a literal B symbol. And this is going to match one or more digits next to a B. So things like this or that. But after that, we're going to have exactly what we have before, right? We have to match the rest of the number now, but the rest of the number, instead of being digits 0 to 9, they could be any of our digits 0 to 9, A to Z, because it's an arbitrary base, which is why we're going to be using $D instead of /D. And this is going to just substitute in this thing so that we don't have to type that out all the time. But if I tab this over, get the spaces lined up, this capture group here is just going to be essentially the exact same thing as we had before, but with these types of digits instead. And that's why I'm formatting it this way, so that you can see it's actually the same thing. It's just, in this case, these digits are not the same digits. And be careful with your parentheses, because notice all of this is in that parentheses, meaning it can follow the like 3B or 10B arbitrary base thing. Next, we're going to have our hexadecimal and octal specific ones, because notice our binary one, our 2B like this, is already, or 0B I mean is the default one. That's already considered here because 0 is a single digit. So we don't need to do it again, but the other ones need to start with a 0, and then they need one of an X or an O. So again, this is saying it needs to be one of these two symbols. And then we can do exactly the same thing as before. And I have to shift these so that they line up. And in fact, this one is it's identical to this. So I can just come in here and yank that. And I probably have too many parentheses. That's okay. I have way too many. All I need is 3 on here. Just be careful with how many you have. And the good thing is, since we formatted it this way, since they all line up, we know it's probably good. Next, what I want to do is on this string, I want to replace all spaces with nothing. And how we're going to do that is we're going to actually use a regular expression separately. And that is going to be the //s. Like I said before, since we're in a normal string, we need double slashes. And we have to then say two regex here to make this a regular expression. And that's going to call a different replace overload. And we're going to replace everything that matches this pattern with nothing. And that's just going to get rid of all the spaces, because we don't want those in our pattern. They're just for formatting's sake. And then we want to convert our pattern itself to a regular expression so that it becomes a pattern and not just a string. Wow, that was a lot. But now we have a pattern to match things that potentially could be numbers in our language. Because again, notice, if you say something like 0b and you put an f in there, well, that's not valid because f is not a valid binary digit. But we'll handle that in a moment once we actually handle the conversion. So then what we can say is if file.nextString, if the next two characters, if it matches, and matches is how we're going to be calling regular expression essentially. We want to check, well, what if the next thing is a period followed by something that is not, that's what this caret means, is not a digit or an underscore. Because we are also allowing underscores in our numbers in order to just separate them out so that if you have a huge number, it just makes it more readable, but it fundamentally doesn't do anything. And we can use the question mark here to say that this is optional. There could be 0 or 1 of these, because suppose hypothetically that next string, we're at the end of the line or whatever. Suppose you put a period at the last line where the next token's an end of file, the next string of 2 might return a single period. And so we still want that to match, although that by itself probably would already cause some other error down the line. But, you know, just to be safe, we can say that this should be like this, and we can say to regular expression to make it a pattern. And so we're checking, are the next two characters, is it a period followed by something that isn't a number? Because if it is, then it's actually a punctuator, and we can call make punctuator, which I haven't implemented yet. What I can do is I'll just temporarily, I'll just say make punctuator down here and do nothing so that I can call it. And we can return. I have a choice of how to format this. All of our make things are going to return units or nothing. So we can just return make punctuator and make it a bit neater that way. So we've just ruled out the case that we have the period operator. So what we can do is we can just take, what do we want to take? We want to take these things that are token.numSims, and not just start sims, but any of the symbols, which includes the uppercase letters that we were talking about before. Then we can make a token. We're going to have to store it though so we can modify it. Token.type.num, because it's a number. And then what we want to do is we actually want to take its string and we want to modify it, which is why we made it a variable and not a value. We can say token string should be equal to token string.replace. And notice, of course, when you call replace on a string, it's not going to actually modify the string, it's going to construct a new one, which is why we have to do the assignment. All we want to do is we want to replace all the underscores with nothing. And we have to do that before we check against our pattern, because notice we didn't put any underscores in our pattern. Now, this is a very liberal sort of use of underscores. I don't care where you put underscores in your numbers, so long as it's not the first thing. So the way that we've done this, you could make a number that looks something like a 3. Like, you could make it disgusting if you wanted to. You could make something like that, and that would be a valid number in my language. You could do that, but don't. Like, I'm not going to enforce it with my compiler. But, you know, because that's the thing. There's certain choices you can make in a language to prevent bad code. But the more you do that, the more restricted people get. And sometimes things that you might think are bad code aren't necessarily bad code. Especially because, notice this. If you have a number like this, okay, the underscore usage makes sense here. But suppose then you have something that's more like this, and you're like, well, that's not a valid use of the underscore, because that's not a valid number. But maybe this number represents a date. And this is like a month and a day and a year or something. And so there's other ways of formatting things. Like, obviously, again, that would be a weird way to format like a date, but you could, you know what I mean? Like that, you could format a date that way. So you should just be careful when you try and restrict your programmers to making only very good code in your language. And now what we want to do is, now that we've gotten rid of all the underscores, we can check if the string of our token matches the pattern that we've created. And if it does, we have to convert the number, because the number could be of an arbitrary base. But if it doesn't match, then it's not a good number. And what we can just say is we can error and say that the token is an invalid numeric literal or something like that. You could just say invalid number or whatever. But now comes the process of actually converting these arbitrary base numbers to something that our compiler can actually use. Because if you're making a compiler or transpiler or whatever, you probably can't handle base 37 just naturally in whatever language you're writing in. If you can, good for you, and you don't need this, but here we go. So this thing is just going to take in a token, and it's going to modify it so that it converts it to base 10. You could convert it to binary or hex, but it fundamentally doesn't really matter what you convert it to, because it's all going to be binary in the end anyway. And it's all going to be compile time constant conversions anyway. So we want to store the string separately so we can modify it. And we can check, okay, are any of these symbols inside of the string, right? Because if there is no B or O or X, then it's not actually in any sort of different number base. It's just a decimal, either integer or float. If there's a B, it's either binary or arbitrary, O being octal and X being hex. So if none of these are in there, meaning if for all of them it's true that none of them are in the string, then we don't need to convert it and we can just leave. And so see what I'm doing here. I'm saying for all, none of them are in. That would be the same as saying, you could also negate this and say that, like, there exists one of them that is in the string, then don't return. But again, it's just like basic sort of logic inversion stuff. We're just seeing if it's true that all of them are not in the string, we return and don't convert. Okay, so the first part of getting the conversion is, well, what number base are we starting with? So we have to get the base. And we can check. This is also part of the reason I'm limiting letters to uppercase. I'm only allowing uppercase digits, and part of the reason for that is it makes these checks really easy, because to check if a number's octal, we can just check, is a lowercase o in the string at all? Because that's only ever going to happen if it's written like this, you know? So we can just check. If O is in the string, well, then the base is 8. And I'm going to store the base as a double so that we can use power.pow on it. Else if there's an X in the string, well, that's just 16. Otherwise, we have to actually get the base. And what we want to do is we want a substring from 0 up until string.index of b, because we don't know how many digits it starts with, so we're just going to take the substring of the string, up until the lowercase b. And then we're going to cast that to a double. So if you have 0b right now, the base is going to be 0. So let's check. If base is less than 1, then base should actually be 2.0, because it's binary. Now here's a choice I make. I choose, because notice every base is supported right now. Every single base you could possibly write, all the way up, is supported, except base 1. So I have 3 choices. 1, I could support base 1, which is essentially tally marks as every number. I'm not going to do that because nobody's going to use that. 2, I could just say, well, if it's 0, 1, or 2, then it's binary, and just make it binary, because 0 is binary and 2 is binary, so... Personally, I don't want to do that, because to me it's 2 separate things, even though it looks the same. 0b is of the family this, whereas 2b is of the family arbitrary base, right? Like, they're both using a b, but they're different things. So my choice is, if base is less than 1, then base becomes 2. So if base is less than 2, meaning it's 1, then I actually want to throw a failure and say that you can't use base 1. Numeric base cannot be 1, because why should it be? There was something else I was going to mention. Right, I said I supported every base, like literally all of them, because I technically do, but you will notice a problem. You have digits 0 to 9, which is, 10 things, and then you have all the letters. So after you get into bases of like 36, 37, 38, you don't have digits to represent every single digit. But that's kind of okay. I could just say you can't use a base that big because you can't represent every possible number in it. But what I'm going to do is I'm just going to support some of the numbers in it. So what that means is you could write like base 1000 and you can use Z's to be your highest digit. You won't be able to represent digits higher than that, but you will be able to represent some of the numbers in that base. So let's see, now that we have this, what we want to do is we want to say, if we have an O or we have an X, and again, we have to use regular expressions here, we want to replace either an O or an X with a B. Lowercase o or lowercase x. Either one. And we're just going to do this so that we can easily split the number. We want to put them all in a form. The O and the X only matters to get the base, and we've already done that, so we can just manipulate that away. Now I want to say that the number is the substring. It's the rest of the substring, right? So the first part of the substring is to get the base. The second part is to get the actual digits. I suppose I could call this digits rather than num, but I'll just call it num. It's not a big deal. Just keep in mind it's of type string. So we want to go up from the index of the b plus 1 so that we don't include the b, and it's everything after that. Then we want to have some result, right? Because what we're doing is we have to calculate the value of that number and store it. So we're actually going to store it as a double. So of course, if you have really huge numbers or really like small precise numbers, eventually that's going to lose precision. But that's kind of okay because most languages are going to have similar levels of precision. You could change this, you could improve this by having some custom type here that can more accurately store things, but for our purposes, this is going to be fine the majority of the time. So I want to get the integer component of the number and the fractional component of the number now. And the way we're going to do that is we're going to take the digits we have, which, keep in mind, might include a period or might not, and we want to split it around a period. Now, if this period doesn't exist, then the split will return one thing, whereas, like an array of one thing, you can imagine. But if it does exist, it will return the array of the thing on the left and the thing on the right of the period. So we can take this and we could say let so that we can operate on the split value, and we can make a pair. This being the thing that will be split into int and frac. And the pair is going to be the first thing, the thing on the left of the period if there is one. And if there isn't one, well, that's why we have to be careful. We can say get or else the thing at 1. And so basically, this is like doing int, this is like doing it at index 1, except if there is nothing there, then what we want is nothing. We're giving it the else condition instead of throwing like a out of bounds exception. So that's kind of it. The first thing here is the integer component, whatever's on the left of the decimal, and here's whatever's on the right. If there is no decimal, it's just an empty string. Now, just for the purposes of making errors, we just want to make a quick error template so that we don't have to repeat this all the time. We're going to essentially be saying that a digit is an invalid base, followed by the actual base we're working in, digit. And since our base is a double, that's going to be weird if we don't display it. If we display it as a double, that's going to be weird. So we just want to make it as a 2int. Now we just need 2 loops. We want to go through with both the character and the index in the integer component and the fractional component. So we can do int.withIndex in order to also get the index. That will be the first thing here, and the C here is going to be the actual digit that we're working with. So now we have to figure out what's the like mathematical value of that character, because if it's something like f, well, what does that mean? Well, the digit is going to be, if it is a digit already, meaning it's 0 to 9, we can just subtract the character from 0. And that will give us, you know, the actual integer value, because the character 0 is one character less than the character 1. So if you subtract these things, if you subtract the character 1 from the character 0 from the character 1, you'll get the integer 1 because they're 1 apart. So we can just simply subtract that from that. But otherwise, the thing isn't a digit, and it's actually a letter. So we have to then subtract it similarly from uppercase A. But keep in mind, A isn't 0. A actually represents 10. So we have to add on 10 to all of those then. And now this gives us the value, the integer value of the digit that we're actually indexing over. Now what we want to check is, well, if this digit is bigger than the base itself, or equal to the base, then that's not a valid digit for this base, and we can just throw a failure and say that this digit, error template, meaning is an invalid base blank digit. I can't spell. Okay. Otherwise, what we want to do is we want to add it to our result. And how do we actually calculate the value here? Well, it's the digit. The way that base systems work, if we have a number like 100, what that's saying is it's 1 times our base 10 to the power of 2 plus 0 times 10 to the power of 1 plus 0 times 10 to the power of 0. That's the calculation. And luckily, we know what these powers are because that's our index within the string, which is why we are looping with the index. So we can add to our result the digit times whatever our number base is to the power of the length of the integer minus I minus 1. Now let me think exactly why we're doing this. If we have the string 100, like I said, then what we have to do is we have to invert it, because the index of the... This is 1 times 10 squared, but the index we have is actually 0. So what we have to do is we have to add 1 to that index, and then we have to subtract it from the total length, because there's 3 characters. So we take the 3 minus the 1, which gives us our 2. And since, like I said, you could also rewrite this as minus I plus 1, but it's the exact same thing. Hopefully that makes enough sense. If you have more questions about that, you can just ask in the comments and I'll gladly talk about it. Similarly, we have to go through the fractional component. It's going to be mostly the same, but slightly different. You could do this in one loop, I think, but you'd have to be very careful with your indices and stuff, so I'd rather just sort of repeat it. Actually, we can just copy. Where's my cursor? Why can't I? What? It's right there because I'm in insert mode. Jeez. I can just come down here and yank this. That moment when deleting something actually copies it. Yeah, that's fine. Okay, so now, after all that, we have literally exactly what we had before. Except we now, when we add our result, it's going to be different because we're not adding the integer component anymore. What we need is, we need the digit times the base to the power of negative I plus 1. So instead of taking I plus 1 and taking it out of the length, this time the index is actually correct. Because now, remember, it would be something like this, right? If we have FF here. Let's just make it simple, 3, 3. This index here is 0, and this one's 1. And the powers we want is actually going to be, what would this number represent? This would be 3 times 10 to the negative 1, plus 3 times 10 to the negative 2. Of course, have your parentheses around there, but that's not really important right now. So our index, we just have to add 1, and then we just have to negate it, because we're working downwards. And that's also why we're storing it as a double. Lastly, there's one thing left to do. We want to actually modify our token because we've just been working with the copy of the string this whole time. And we just want to do 2 things. We want to set it to the string, or actually we want to set it to the result, but keep in mind that the result is a double, but the number that is represented by the token might actually be an integer, so we don't actually want to change anything about it. We have to check, is there a period in the number? Actually, we could just say if num.isInt, right? Because we I believe that we implemented that, didn't we? I'll check that out in a moment. Basically, we'll print out the result. If it's not isn't. Yeah, so if it's an integer, we want to take the result and cast it to a long. I'm choosing long so that we have as many digits as possible. Otherwise, we just have the result itself. Did I make it a field? Because I would have loved if I made it a field. No, but I'll go ahead and... Oh, I'm saying num. Oh, because what I was saying before is there a period in the num? But we could also just say token dot... We could just check if the token is an int. But I'm also going to change this to a field, because isInt, it doesn't feel like a function to me, it feels like a field, so I'm going to go up to token and just quickly change that to a value with a... It doesn't need... It should it have a getter? That's a good question. We're constructing the string... Well, the string doesn't exist until after, so to be safe... No, the string does exist by the time we do this. Just to be safe, I'll make it a getter, but I don't think it has to be. Let me get rid of the parentheses here. Go back to our Lexer. Okay. So, wow. I think that should be it for our numbers now. Let's go try and test things. If I go up to our test, we have, let's just have like some integer here. Let's have some like binary number. Let's have some hexadecimal number. Let's have some base 3 number with like a 0.1. Let's have some base 4 number with a like a 3 point, just something, right? Something that could test it. You would probably want to be more exhaustive and have better sort of tests. But so you see all of these work, and here's actually the interesting thing, right? So the way I've chosen to do it is I'm not keeping track of the original like token. You see that these are changing. So the first number is the same, but the second number here, this binary number, well, that's just 9. And does that check out? Because we have a 1 plus no 2s, no 4s, 1, 8. So 8 plus 1 is 9, and it's an integer. This 4 F's in a row in hexadecimal is actually this number, which seems right. 3b.1 gives us 0.333 with a lot of precision that we didn't have to type by hand. 4b 3 point just gives us the expected decimal 3, but of course decimal. And we get our new lines and everything. Let's try getting some error, something like, what if I say binary, but it's 2? 2 is an invalid base 2 digit, exactly as we would expect. Now, it is highlighting the entire thing. You could hypothetically highlight the specific character, but that would be, you'd have to be a bit more careful with how you do that. That's something you could do, though, to make this even better, I suppose, because if it pointed the exact thing, but it should also still be pretty obvious just by pointing out the number. And now if I change this to a 1, it should say numeric base cannot be 1, and since it's a failure, we only get 1 of them. If I say 3, though, I didn't write it. And then it works, and it just gives us exactly as we would expect. So I hope you guys found some of this interesting. So what did we do exactly? We now have spaces handled, we have comments handled, and we have numbers handled. But not only do we have numbers, we have arbitrary bases of numbers. We have hexadecimal numbers, octal numbers, binary numbers, and any base that you want other than 1. And technically 0, because base 0 doesn't make sense, but yeah, that's there was something I'm trying to think of. I feel like every time I try and talk, there's just something that I can't remember exactly what I wanted to say. Hey guys, so if you're interested in how long it's been, you can look at the top of the screen, but I finally remembered what I was going to say. Oh no. Oh my god, I really almost just forgot it again. I just had to cut out like a minute of a pause of thinking. But what I remembered after all this time is to mention I'm not currently supporting like scientific notation in numbers. Finally, I said it. Oh my goodness. Basically, in a lot of languages you can say things like, I don't know, like 1.1 to the power of 5 or something. Like you can use E to represent a power, and you can use P in other languages to do like binary sort of representations. Currently, I'm not going to have that syntax in our numbers, as you see, because we built them. In the future, we might add something like that, and that's something you probably would want to add to your language so that you can add sort of really crazy numbers like that. God, I can't believe how long it took me to remember to say that. Anyway, I'll go back now. But I hope that with my inability to talk and type that you found some use in all this. And next time we will implement even more of our Lexer. It's kind of funny how many videos this is taking, but I'm hoping you guys seem to be liking the amount of depth I'm going into, so I hope you guys enjoyed this one as well. I'll see you in the next one.